Thank you for being here. Thank you for having me here. I'm Chris. I work in a team that develops hydraulic simulation software for roof drainage systems. That's Flachdachentwässerung. And we developed a while ago a classic machine learning solution based on supervised learning and neural network. The solution was aimed to support our users in finding the right dimensions for these roof drainage systems. However, last year, about the beginning of last year, we had to realize that we won't be able to improve our solution any further. Meaning, even better data sets, larger data sets, better algorithms, more compute power, all of that wouldn't be of any substantial help anymore. Nonetheless, our experts often find solutions to our planning problems, essentially by playing around, a key ingredient of reinforcement learning. Reinforcement learning is a form of machine learning that does not depend on a training data set, but instead uses the interaction with an environment. And we will dive into the topic in a playful fashion, illustrating the way the algorithms work by the way a child learns to play a new game. In the second part of the talk, we will then apply this approach to our hydraulics problem. And we will see that using reinforcement learning algorithms, we were able to reduce the fail rate by more than 70%, way beyond any of our expectations. And then in the last part, we will dive into, or have a short dip into the implementation side, and that's where we'll see how our project almost died on the last mile. So let's get started. Children are true masters at learning new stuff. Give a child a new game and it will immediately start by playing or pressing some random buttons and seeing what happens. It's interesting to note that you don't have to explain to a child how a game works. So figuring it out is part of the thrill. Also, once the child has mastered the game, it usually can't tell you why exactly it took this or that move. So they essentially play in an intuitive fashion. And we will rediscover these two properties also in the resulting strategies developed by reinforcement learning algorithms. As a running example, I chose a simple game called Snakes. I chose it because on one hand it's easy to understand, but nonetheless it takes quite a bit of strategy to play it well. So let's take a look. I play the game by moving the snake around using the arrows, and for each step taken I get a reward. When I eat the fruit I get a high reward of 100 points, and otherwise just -1. You see the reward on the upper left-hand side. The game ends once the snake either drops off the board or collides with its own tail. So initially the game is very easy. You just head greedily for the next available fruit and eat it. But the longer the tail gets, the more difficult it gets. And suddenly, when you make a bad move now, you end up in a losing position down the road. For example, just now I clearly made a mistake. You can see, although I can still move, I can even eat fruits, but the end is near. So to win this game, I need a strategy, or to play this game well, I need a strategy which is able to look quite a few steps into the future. So let's see how a child might try to learn this game and acquire a reasonable strategy. So initially, the child has no clue about the game. So it will just start by pressing some random buttons and seeing what happens. These buttons, we also call them actions. And for each action taken, we get from the game engine a feedback in the form of a new game state and a reward. The reward tells us how good or bad our last move was. And of course, our goal is to maximize the sum of rewards over the whole game. And the game state is the only input the child gets to decide which action to take next. So as the child keeps on pressing some random buttons and seeing what happens, at some point it will have a lucky strike. Meaning it will press a button, resulting in a high score, in a large reward. So learning from this positive experience means that from now on the child will try to take the same or choose the same action again whenever it finds itself in a similar game state. And of course the opposite can happen as well. So it will choose an action resulting in a high negative reward, and learning from this bad experience means that from now on the child will try to avoid taking this action whenever it finds itself in a similar game state. And as the child keeps on playing like this, it will continuously improve its gaming strategy. And this gaming strategy, or this thing that the child is learning, is also called a policy. And we view the policy as being separate from the learner. So the policy is the guy who decides which action to take next, based on our current game state. An action can be very simple, like one that just chooses a random action. A policy can be very simple, just one that chooses a random action. Or it can be very intricate, like one that always reaches the maximum number of points. So if it's the task of the policy to be the decision maker, it's the task of the learner to improve the policy once the game is over. Thus, like this, with each game played, we get a new and updated policy. And thus we end up with a whole sequence of policy, one better than the other. And it is exactly the idea of reinforcement learning to learn by mimicking this behavior of the child. So the idea here is to design an algorithm which is able to improve an existing policy only through the interaction with the gaming environment. Now that's a pretty bold statement, so let's take a closer look at it. It means we can start with a game engine, with a game inside about which we know nothing. We take an initial random policy, so there's no knowledge about the game inside this policy. And we just fire up the algorithms. But we don't give the algorithms any additional clues about the game. We just let them start and play. And after a while, the promise is that we will end up with a policy which is able to play the game rather well. Sounds almost a little bit like magic. So let's take a look how this magic maybe works a little bit in more detail. So we start the engine and we get an initial game state. Since we have no clue about the game yet, we use an initial random policy. And to keep things simple, let's assume that our random policy has the same probability for each of the actions, which we represent with a gray background behind each of these actions. So we now let the policy decide which action to take next. It randomly chooses to go left. We send this to the game engine, and as a feedback, we get a reward, -1, and a new game state. The snake has moved by 1 position. So our goal is to improve our policy once the game is over. To this end, we must be able to remember what has happened. Thus, we store everything on the side, meaning we take the state we were in, the action we took, and the reward we got, and record everything on the side. And now we're ready to take the second step. Again, the policy chooses an action. This time we eat the fruit, we get a high reward, and we record everything. And we keep on playing. Once more, this time the policy chose to go up. We therefore drop off the board, we die, and the game is over, which we record as well. Since the game is over now, it's now time to do the policy update. And we do the policy update stepwise, starting with the last step. Clearly, our last step was a bad move. Well, we got a high negative reward, we died, and the game is over. So learning from this bad experience means that from now on we will try to avoid taking the up action. And we learn by changing the probability of the up action. So let me repeat this. This is actually the crucial step of the algorithm. We learn by changing the probability of the action we took for the state we are in. And that's what we will keep on doing like now for the rest of this policy update. So now we've changed so since that was now a bad reward, a bad experience, we now reduce the probability, which we represent with a red background. Now we're done with our first step and we are ready to move on to the previous one. Well, in the end, our goal is to find a policy which is able to look quite a few steps into the future. Thus, we must not only take our current step into account, but all steps from now to the end of the game. And of course, we want to update the probability for the action we took. So we do this, taking the other steps into account, by taking the sum of rewards from now to the end of the game. In this case, that's 100 points from our current step and minus 50 points from our next step, yielding 50, and we consider 50 to be a nice value. And therefore, we now increase the probability of the action we took, which we represent with a green background. Now we're done with our second step, and we move on to the first one. And here the same story. We compute the sum of rewards, 49, nice value as well, and we keep on updating our preference for the left action. Since it's a nice value, we increase our preference. And we're done with our policy update, and now ready to move on to the second game. Of course, for the second game, we will now also use our new and updated policy. But to keep things simple, let's assume that we use the same game state again as we did in the first game. Do you still hear me? Sometimes? Okay. So now we use our new and updated policy. Note that for this game state, we've already learned in our previous game something about the left action. We have an increased probability. But we let the policy decide, choose to go left, and now we keep on playing and recording as we did before. Now in this state, we already know something about the up action. It was a bad choice, so we have a reduced probability. We let the policy choose. This time it chooses to go down, and we keep on recording. And now it chose to go left, and we drop off the board, and the game is over. Time for our second policy update. Now, again, we compute the sum of rewards, but this time the sum is just like consisting out of the minus 50. So it's minus 50, a bad value, and therefore we decrease our probability for the left action. And we keep on doing our policy update. Now remember, we always only do the update on the action we took. Here we took the down action, we compute the sum, and we reduce our preference. Although here we know something about up action, we don't care about the up action. We ate the fruit, we get now a nice reward of 49, and we increase our preference. Now this step here is the most general case, so let's take a closer look at it. The problem here is that we choose the left action, and in our previous game we already learned something about the left action. So let's see how we deal with this situation. We start by computing the sum of rewards, yielding 149, which is an incredibly high value. We've never seen such a high value before. So in a naive update, we would now increase our preference for the left action drastically, maybe to a value like this. But by overriding the value we saw before, we forget everything we've learned so far. And of course, we somehow want to incorporate the knowledge we acquired in our previous games. So we must not override the value. So what we do is we take some form of a running average between our previous preference and the new one we learned in this game. So we settle for some value in between. And that's actually how we always do our policy update. And here again, we calculate the sum of rewards and take some form of a running average. And our second game, our second policy update is over. But instead of playing a third game, let's take a step back and see where we are. So we have this notion of a policy. The policy is the guy who decides which action to take next, based on our current game state. Thus, we can view a policy as a map from game states to action probabilities. And of course, we can readily represent such a map using a lookup table, indexed by the game state. And we started with a random policy, meaning we initialized this lookup table with some random values. Then we use this lookup table to play our game, looking up the probability of the next action to take. And once the game was over, we modified the values, our probabilities, or our preferences, meaning we modified the values in this lookup table. Like this, we got an update of our lookup table. We used this one again to play the game, and updated that one after the game as well. And if you keep on doing this, like for many games, like for 100,000 games or 1,000,000 games, then we will end up with a nice set of action probabilities for each of the game states. And these action probabilities actually represent the essence of what we've learned. That's kind of our condensed experience. That's really what we've been looking for. That's our gaming strategy. And of course, I can take an approach like this and turn this approach into an algorithm. And such an algorithm might look something like this. So we start by initializing our lookup table with some random values. We then use the lookup table to play the game, and we can record everything on the side, like the state, the action, and the reward. Once the game is over, we enter into our policy update. For each step taken, we calculate the sum of rewards from now to the end of the game. And if the sum is large, then we increase the preference for the action we took for the state we are in. And if the value is small or negative, then we decrease our preference. So that's how we update the values in our table. We do this for each step, and we do this for many games. And I used an algorithm like this to train a policy for the snake game. So let's see. So I now started a well-trained policy. I took my hands off the keyboard, and hopefully the policy will start to play. Note that the snake does not top off the board, at least so far, so it has somehow learned that rule. It's also kind of interested in the fruits, but it's not eating the fruits in an over-eager fashion, so it looks like it has some strategy there. And it's looking good. And it won. To be fair, usually the snake wins in about 50% of the cases, and in the remaining cases, it usually gets a rather high score. Now let's compare this to an initial random policy. Okay, so this one chose just to jump off the board. Let's try again. Yeah, clearly, you see that the snake has no clue about the game. It's just running around erratically, not knowing what to do. So, and the difference between these two strategies, that's really the achievement of these reinforcement learning algorithms. That's what they did. And that's what we are really looking for. Now, this looks like a fantastic algorithm, as we've just seen. But the bad news is, this is not going to work in a real-life scenario. It's really just a nice idea. The problem is that in a real-life scenario, you typically have way too many game states. If you have a lot of game states, then you will end up with a huge lookup table, requiring a lot of memory. And if you have a huge lookup table with a lot of memory, then you also need a lot of compute power to do all these updates. So it takes way too much time. Even in the case of the snake game, we have about 500,000 to 1 million different game states. And when we increase the board size, then we end up in a combinatorial explosion, so it is simply not feasible. So, but at the core of the problem sits this lookup table. And we only use the lookup table to represent our policy function. So the key idea here now is to drop the lookup table and to use a function approximator instead. And neural networks are excellent function approximators. So let's see. If we replace the lookup table with a neural network, then instead of updating the values in the lookup table, we will now have to update the weights in the neural network. And that has the nice side effect that it only has a minimal impact on the algorithm. So let's first take a closer look at the neural network side and then at the algorithmic side. So whenever we have a neural network, we must first choose a network architecture. But through the network architecture, we directly control our memory requirements, and we directly control, therefore, also our key problem we had with our lookup table. But when we use a neural network then as a policy function, then we must encode our game state as a vector, which we then send through the network, and as an output of the network, we want to have for each game state one value representing our preference. That's the out value for the corresponding action. And then we turn these values back into probabilities using softmax. So all our algorithm really has to do is find the right weights for this neural network. And that's the task of the algorithm. So let's see. We want to start with a random policy. Having a neural network, that means we initialize the weights with some random values. We then take these weights, or this network, and play the game. And once the game is over, we enter into this policy update mode. Now let's assume that in our current step, we took the up action and we got a high reward. So that means that we want to increase our preference for the up action, which means we want to increase our probability for the up action. So to this end, we now must find a set of weight changes such that for the current state, the out value for the up action increases. But since we have a neural network at hand, there's a readily available function which exactly computes this weight change, namely the gradient. So all we have to do is we take the weights and we add the gradient to it. And we're done. Almost. But sometimes this sum of rewards is very large, and when the sum of rewards is very large, then we want to increase our probability a lot. And sometimes the reward is very small or negative, and we want to decrease our probability. To this end, we simply multiply the sum of rewards with the gradient. Now we're almost done. What remains is we somehow have to control the impact that our policy update has on the weights. Because like initially, the weights are just random values, so we want our first games to have a strong impact on the weight changes. But after a million of games, our weight changes, our weights contain all the knowledge from the previous games, so we want the last game only to have a very small impact. So to this end, we use an additional factor, it's called the learning rate, which we also multiply with the rest of the equation. And initially, the learning rate is like 1, and then we continuously decrease it towards 0 when we reach the end of the game. So this is essentially the algorithm we are looking for. And there's a whole family of algorithms that work like this. This family of algorithms is called the policy gradient algorithms. And they are called like this because what we're doing is we use a neural network to directly represent this policy function. And we use a gradient descent to do the approximation. So if someone of you is interested in the math behind, please let me know. I'll be more than delighted to go into the math with you. But now let's move on more to the application side. Oh, sorry. I work for a company called Geberit as a consultant. It's a sanitary technology company with about 12,000 employees. And Geberit produces in particular pipes and stuff to get the rainwater off the roofs, of flat roofs, so-called siphonic systems. However, it is surprisingly difficult to find the right diameters for these pipes. It's actually so difficult that as of today, there's no feasible deterministic algorithm which could compute these diameters. That's why we had to resort to traditional heuristics and classical machine learning to support our users. And using a combination of these two, we were able to reach a success rate of 93%. Meaning in 9 out of 10 buildings, we are able to automatically find the right dimensions for all the pipes in these systems. That's a pretty good value. And you might say, hey, what do you want? I mean, that's pretty much the end of the road. The problem is the remaining 7%, because in the remaining 7%, we find the most attractive buildings. These are typically very large buildings generating big revenues, or the most prestigious buildings, yielding fantastic marketing stories. And are all buildings in there which drive our users nuts because they're so difficult to find a solution for. And a while ago, I gave at another machine learning conference a talk about our classic machine learning approach. And there, someone in the audience posed a question about dynamic programming. Dynamic programming is a precursor of reinforcement learning. And that kind of ignited the idea to use reinforcement learning to attack the remaining 7%. However, in order to see how this works, we need a little bit of background in hydraulics. Nowadays, flat roofs are everywhere. And to protect these roofs, we must be able to deal with the largest precipitations that take place only once every 30 or 100 years. On roofs like these, it rains up to 500 liters per second. That's about 200 bathtubs dumped every minute. Nonetheless, the water level must not rise above 10 centimeters, because otherwise the water gets too heavy on the roof and the roof might collapse. Thus, to get these water masses safely and reliably off the roof, we need, on one hand, a carefully designed piping system, and on the other hand, a hydraulic trick. Bless you. And this hydraulic trick is based on negative pressure. Using negative pressure, we can literally suction off the water off the roof. Thus, the dangerous water masses, they cannot accumulate anymore in the first place. And the whole thing essentially works like this. By choosing special diameters for these pipes, the pipes fill up fully during heavy rains. Thus, we get a closed water column on the verticals, resulting in a negative pressure, suctioning off the water at the outlets like a vacuum cleaner. Also, thanks to these specially chosen diameters, we get very high flow velocities inside the pipes. Thus, the pipes cannot clog anymore, and we end up essentially with a self-cleaning system. Traditional or conventional roof drainage systems need a slope, which is very difficult to install and also takes up a lot of space. Siphonic systems don't have this drawback. And of course, there are many more advantages to it. So if you're by now enticed to build your own siphonic system on your house, let me know. I'll give you all the gory details. But let's make an example. Let's design a piping system for this building here. This building here has about a size of 7,000 square meters, yielding about 200 liters per second. So to find the right diameters, the ones resulting in this negative pressure which suctions off the water, we need a software, like the one developed by Geberit, which is called a ProPlanner. So let's take a look. So up here we have a schematic graphical user interface. These elements here are called the outlets. That's where the water enters the system. And then the water flows through all these pipes and leaves the system down here. When I now start the computation, it will proceed in two steps. In the first step, we will use heuristics to try to find suitable diameters for these pipes. And in the second step, we then start the hydraulic simulation using the diameters chosen during the first step to see if the negative pressure really builds up and if the system is working. As a result, we get down here a hydraulic list. And each row in this list represents one pipe. So here in this column, we see the result of the heuristics. That's the diameters chosen for each of the pipes. And here on the right-hand side, we see the result of the hydraulic simulation. And as it is with heuristics, sometimes they work, sometimes they don't. In this case, they didn't. And for example, here we see we should reach about 200 liters per second, but we only reach 177. So that's not good enough. In a case like this, now I, as the end user, must choose better diameters. Hopefully using my hydraulic knowledge, my expertise, my experience, and in particular my gut feeling. So I just choose, sorry. I just choose a pipe, maybe this one here, and I change the diameter, essentially by guessing. And I start the computation. Now that helped a bit, but not a lot. So I have to go on, choose another pipe, now maybe this one here, and start another computation. Now what's nice is we've solved the problem up here. What's bad, we got a new problem down here. And this is almost like a vicious circle, and it's very typical for the work that the hydraulic planner has to do. It can easily take a couple of hours for a difficult system, even if the user is quite experienced. And it's a very bad idea to build or construct a piping system whose simulation shows errors. For example, imagine if the hydraulic simulation shows that the negative pressure is too high. Then during heavy rains, the pipe will literally collapse. That looks like a giant fist squeezing the pipe together. Thus the water stays on the roof, gets too heavy, and the roof collapses. If the simulation shows too slow a flow velocity, then the pipes will clog, water stays on the roof. If the roof resists and does not collapse, water spills over the sides of the building and damages the facade. You really don't want to go into these kind of problems. But by now we know enough about hydraulics to apply reinforcement learning. So let's see. To use reinforcement learning, we now must turn our hydraulics problem into a game. Which means we must define a set of actions, define a game state, a reward function, and of course we need a game engine. In the game engine, that's where all your business logic resides. In our case, that's the hydraulic simulation. That's why we use ProPlan as our game engine. So let's start by defining the actions. In the case of the snake game, that was easy. That's simply the buttons. In our hydraulics case, we must be able to move up and down the hydraulic list and then change the diameters for the selected pipe. Thus, we can choose maybe these 4 actions. And they are sufficient. So like with these actions, the algorithms will work. But it turned out that our experts often jump directly to the next error. Or they directly jump to the next vertical pipes, because vertical pipes have a very strong impact on the overall hydraulics. So once we've added these convenience functions, the resulting strategies had quite an increased success rate. So it might be a good idea to think about convenience functions, but I would recommend to start with a minimal set of actions. Now that we have the actions, we need the game state. And remember, the game state is the only input our policy gets to decide which action to take next. So the game state must contain all the information that is needed to make this decision. In the snake case, that's simple. That's simply the board, which we can either encode as an image or as a matrix. In the hydraulics case, we use the hydraulic list because we notice that our users don't look at the graphics anymore when they start to fiddle around with the diameters, which is a strong hint that the graphics does not contain any relevant information to make this decision. But initially, we did not include the error coloring, so the yellow and the red backgrounds, and it worked. But for our end users, these error colorings are quite important. They're an important visual clue. And here, once more, once we've added this kind of convenience information, it also helped the algorithms a lot. In general, once you've designed your action set and your game state, it might be a good idea to validate your design. And one way to do that might be you ask an expert to play the game you've just defined. If your expert is able to play the game and win the game just by choosing one of the actions or actions you've defined and just by looking at the game state you've designed, then you might have a good starting point. If it's difficult or not possible for your experts, you maybe want to rethink your design. Now let's move on to the reward function. Actually, designing the reward function is probably the most subtle part in the whole thing. Because depending on its design, you may get very unexpected and very surprising results or resulting strategies out of the algorithms. As an example, assume that we didn't give any point for eating a fruit in the snake game case. So we only give points for winning the game. Now life becomes quite miserable for the snake. Because we start with an initial random policy, it's very unlikely that the snake will ever win the game. If it doesn't win the game, and winning the game is the only point where we get a reward, then the life for the snake is just a sequence of painful steps ending in death, never having any positive experience. Thus it becomes quite a clever strategy for the snake to jump off the board as fast as it can, avoiding the pain of life. In our hydraulics case, we choose the following reward function. We simply give 1 point for each error less and -1 point for each error in addition. And that's the actual reward function that we use in our production system. However, originally we chose a slightly different reward function, namely the following one. We give 1 point for any reduction in errors independent of the error count, and -1 point for any increase in errors, also independent of the error count. And that resulted in a surprising, at least for us, in a surprising policy. It went like this. It started happily by reducing one error after the other. For each error reduction, it harvested 1 point. Once it got close to 0 errors, it made a huge mistake, generating many new errors, and then happily starting again to harvest the points. So like this, it was able to reach arbitrarily high scores just by continuing this game, but never reaching or never finding a solution. Clearly not what we wanted. So often it is very tempting to put a lot of cleverness into the reward function. But it seems that the more cleverness you put into the reward function, the more surprises you get out of it. But on the other hand, if you make the reward function too simple, as we did, then it doesn't work either. So it's kind of a little bit living on the edge. But now we have almost everything in place. So we have the actions, the reward function, the game state, the engine. The only thing that remains is we must find a network architecture. And to find the network architecture, we simply selected a different number of architecture and tried them out. In the end, it turned out that the most simple architecture actually was roughly as good as the other ones. So we went for the simplest one, which I'm afraid just consists of one hidden layer. But it was good enough, so we went for it. And then we did the training and integrated everything into our software. So let's take a look. So since we have now a game, there must be a gaming console, which you see here. Our users in the production system don't see this console. So. And here we can play now the game manually. So I can move up and down the hydraulic list. I can change the diameters. Whenever the diameter is changed, a new hydraulic simulation is performed. And of course, I can jump to the next error, cycle through the error, or jump to the next vertical pipe. Now, let me undo all these changes, and we let the policy play the hydraulics game. Now, when this optimized computation runs, it proceeds in 3 steps. In the first part, we use our traditional heuristics. If they don't find a solution, we start our classical machine learning, which is about to start now. And once this is over, then our reinforcement learning starts. So if the other 2 don't find a solution, then reinforcement learning must jump in, which has happened right now. Here on the upper right-hand side, you see the total reward. That's essentially a representation of how many errors the agent or the policy already resolved. And down here, you see the currently selected pipe. The way this goes up and down looks pretty much like an expert trying to find a solution for the problem. And now the algorithm or the policy has found a solution for this hydraulics problem. We have roughly 7,000 clients installed all over the world in more than 40 countries. But only few of our users, maybe just a dozen, reach consistently a success rate above 99%. And the typical user, one having maybe just 2 or 3 years of experience, probably would need a couple of hours to find a solution for this system here. And a novice user probably wouldn't even have a chance to find a solution. So this is really a big help and lowering the barrier to use our software for our users. Now, using this approach, we were able to reduce the fail rate by more than 70%, resulting in an end-to-end success rate of 98%. So that's pretty good. But maybe you noticed I said, well, that's how we designed the game, and then we put it into our software. So there's the little part of implementing and deploying the whole thing in there. So let's take a closer look at this part. So to do that, we must implement all these elements you see around here and find the suitable algorithms. Assuming you're not a reinforcement learning researcher, and then you probably have your own problem at hand and you just want to take your problem and apply your algorithms to this problem. If that's your use case, then probably you will start with the game engine. In reinforcement learning speak, the game engine is also called the environment, which means you have to define you have to find the simulation environment. You must define the actions, the reward function, and the game state. Once you have this in place, you can ask your expert to play the game, because that's all you need to play a game. But now you just need a human expert to play it. So now that you have the game engine, you're ready to apply the reinforcement learning algorithms. And there are many different algorithms. We just saw one family, the policy gradient family, but there are many other families like Q-learning or actor-critic-based systems, etc. And in each of these families, there's a ton of different algorithms, and there are many different implementations. And it may be very fun to do your own implementation, and the algorithms look deceptively simple, typically just half a page of code, or at least of pseudocode. But I would strongly recommend, if you're not very used into this area, to take a reference implementation. And there are a couple of them. One is by OpenAI. Another one is called TF Agents by Google. TF Agents is a very new one. It's just was published about 2 or 3 months ago. OpenAI Baselines is the reference implementation, which was published about 2 years ago, 2.5 years ago. So now that you have this general implementation, the implementation of the algorithm somehow must interact with your gaming engine. In particular, the algorithms must somehow discover what kind of actions you have and how your game state looks like. Are your actions discrete or continuous? Like in the Snake game, you have discrete actions, just pushing one of the 4 buttons. But when you like steering a helicopter, you will more likely have like continuous actions, and also for the game state. So to facilitate this interaction between the algorithms, or to isolate the algorithms from the environment, there's a framework also developed by OpenAI, which is called CHIM. And almost all algorithms are able to communicate with CHIM, and therefore, if you implement your own environment with CHIM, then you have a good starting point to apply all these algorithms. Essentially, all you have to do to implement your own gaming engine is you must only implement these 3 functions. So the first one is the init function, which essentially returns a description of the actions you've designed and the game state. That's how these algorithms discover how they should interact with your game engine. Then from a playing point of view, the most important function is the step function, which you have to take your current game step, you take the action that is passed to you, you perform one game step, and you return the reward and the new game state, as well as a flag indicating if your game is over or not. So if you just jumped off the board. And because these algorithms play a lot of games, there's also a reset function to reset your game and start a new game. That's all you have to do. In our case, it was a little bit more difficult because our simulation software is written in .NET, and all this stack here is typically written in Python. So you will write your gaming environment in Python, most likely. So in order to close this gap, we had to use a bridge between Python and .NET to forward all these calls into our .NET environment. Now we have almost everything in place, but there's still the policy missing. And the policy is represented by a neural network. And this neural network is injected into these algorithms. So most likely you will have something like a main algorithm or your main method, whose task is to create your neural network, to build up your neural network, and then pass this neural network into the algorithm. Of course, your neural network should somehow be consistent with the game state you're using in your environment. And everything, like in particular this neural network stuff, is based on TensorFlow. Now that we have the whole setup, we're now ready to do the whole training. And as a result, we get the trained neural network up there. And we're ready to go to deployment. However, imagine if you take this image and you go like to the global architect and you're telling him, okay, I'm having a .NET application, but now I'm going to add TensorFlow to it and Python and all resulting dependencies, he may look like this. And actually, I didn't dare to do that. And then suddenly it dawned to us that we won't be able to do this deployment. That's where our project almost died, because there's no way we're going to do a deployment of Python and TensorFlow on our 10,000 clients. I can't imagine that this is going to happen. And now something has happened as well. I couldn't imagine that as well. If there's someone from the video team, help would be appreciated. Otherwise, I just keep on telling you what happened like this. So we can't deploy our Python and the TensorFlow thing to the world. But then to the rescue came a talk by Oliver Zeigerman, who's also giving talks here at the conference. And he presented a way to evaluate the neural networks on the edge, like in a browser, once you've trained them. And he kind of opened my eyes that it's possible to evaluate these networks without TensorFlow or anything else. So now the idea was, or the observation was, that if you can take this network, that's where the policy resides. And all we need is essentially just this network and the weights of this network. And so the idea is now to scrape off the weights out of these networks, store them in a .NET file, and then when we start our application, we read these weights in, we rebuild this network, and then evaluate the network by hand. It's not really evaluating by hand, but because we have because our software also contains a lot of 3D or a CAD-like system, we have a lot of matrix computations and vector libraries and stuff like that. So that was implementing the evaluation of the neural network was relatively easy. So that was in the end our approach. We scrape the weights out of the neural network, store them in a file, read them in, and then evaluate the network by hand. This has the nice advantage that from now on, we don't have to increase our technological footprint on our clients. It's just what we had so far. So it's the global architect wouldn't even notice what's going on. So to wrap things up, like if you have your own problem at hand and you want to use reinforcement learning and you think this might be a good idea, probably you would want to start by trying to turn your problem into a game, which means you have to define your game state, your actions, and your reward functions. Once you have that in place, you can start the algorithms, and they will start on an initial random policy. And then they will play your game and try to improve your policy continuously. One big advantage of reinforcement learning is that you don't need a training data set. So there's no problems with data acquisition, data combing and cleansing, and all that stuff. But on the downside, you do need a gaming engine, which kind of then generates this data you use to train the network. And typically, it doesn't have to be either reinforcement learning or supervised learning. In our case, it proved to be quite fruitful to use them hand in hand or side by side. So in case you embark on your own reinforcement learning adventure, I would be very excited to hear what you're up to. Please let me know. Send me an email, a WhatsApp, give me a call, whatever. Also, if down the road you have some questions, I'll be more happy and try to answer your questions as best as I can. And of course, if you have questions now, I'll do my best. Thank you.